take an example of three-dimensional IR. And while doing this, what we will do is we will take the scenic route and we will learn something that is very useful to us, that is how to use the descent of symmetry to make our job a little easier. As you understand, this is such a small molecule, right? Such a small symmetry point group, even that took us almost 1 hour. So if you keep on doing this, just imagine what will happen if you want to work out something for, say even naphthalene. Okay, I am not even talking about bigger molecules. So we need to find shortcuts, that is what we will try to do. So 3D IRs. So let us take MH6. What is the point group of MH6? Octahedral. How many symmetry operations are there in octahedron? 48. So let us see if we can work with a fewer symmetry operations today. So I will decrease your agony somewhat by giving you the answer. The gamma that you get, okay, I am talking about this molecule, okay. MH6, maybe you can copy it so that we are sure about the directions of x, y and z. Please copy the structure. And write down 1, 2, 3, 4 also. So along z we have 1 and 2, along x we have 3 and 4, along y we have 5 and 6. You are free to draw x, y and z in whichever direction you like. But just to be on the same page, make sure that 1 and 2 lie along z direction, 3 and 4 lie along x direction, 5 and 6 lie along y direction. Okay. So how many orbitals are there now? We are still talking about sigma bonding. 6. So 6-dimensional reducible representation, right? That breaks down into A1G plus EG plus T1U. Right? You can work it out yourself and satisfy yourself that this is what indeed happens. Okay? And what we will do is, we are going to focus on this T1U. How many symmetry operations are there, you said? 48, right? That would be very tedious work. So now let us learn how to use the shortcut. The shortcut is available in the form of descent of symmetry. Descent of symmetry. That is what we are going to do here, and we are going to use not the full OH group, but rather the subgroup O. And in case you are wondering what I am talking about, this is OH and this is O. This is O. Okay. What do we have in OH? We have E, 8C3, 6C2, 6C4, 3C2, I, 6S4, 8S6, 3 sigma H, 6 sigma D, 48. What do we have in O? E, 8C3, 3C2 equal to C4 square, 6C4, 6C2. Do you see that O is actually a subgroup of OH? Whatever is there in O is there in OH, right? But the advantage of working with O and not OH is very clear. How many symmetry operations are there? 1 plus 8, 9 plus 3, 12 plus 12, 24. Half the number of symmetry operations. So for this purpose, we are going to work with O. And before going there, I want to show you, I want to talk a little bit about descent of symmetry. I hope you have not completely forgotten this picture that we had flashed 2-3 times wrongly and at least once correctly. Well, I had goofed up while drawing that diagram that time, but Carter hasn't goofed up. Okay? So, this is a manifestation of descent of symmetry. You start with Ma6, that is OH, and order is 48. Then what you do is you just substitute these two A's in axial position by B's. What is the symmetry point group now? It is D4H, right? And D4H is a subgroup of OH. H is only 16, actually it is better than O, but here we cannot use that, we will still need to use O, we will come back to Y. And then what you do is you substitute this B by C, then it becomes C4V because the horizontal plane is lost. And from here you can go to C2V if you substitute this by C and substitute these two by B. So, this is your group subgroup relationship. By chemical substitution you can go on lowering symmetry and you can go from a group of higher symmetry to a group of lower symmetry. Okay? And all these groups of lower symmetry that we can arrive at by simple substitution from here would be subgroups of this bigger group. I think we had discussed this briefly earlier also. Okay? And this is one kind of subgroup, this is another kind of subgroup. You cannot come to C3V from C4V, for example, because that C3 axis is not even there in C4V. Understand what I am saying? C3V is not a subgroup of your D4H, because D4H does not have a C3 axis, right. So, it depends on which symmetry elements you have sacrificed by substitution. So, from OH you can come to C3V directly, no problem. What you have done is you have retained the C3 axis, but once you go from OH to D4H, you have already sacrificed the D3 axis, C3 axis, right, it is not there anymore. So, from here you cannot go directly to C3V. So, C3V is not a subgroup of D4H, it is a subgroup of OH, D4H is a subgroup of OH, C4V is a subgroup of OH as well as a subgroup of D4H. From D4H you can go to C4V. And what is the meaning of subgroup? That means some of the symmetry operations of the big group, original group, are retained, some are gone. Okay? Now, so what effect does this have on the character table? What effect does this have on the character table? Some of the symmetry operations are retained and some are gone. Let us see what effect it has on the character table. So, we are talking about now D4H, for now neglect this part. These are all the symmetry operations that are there in D4H. Okay? We just discussed this, isn't it? E is big enough? Yeah. E, 2C4, C2, 2C2 dash, 2C2 double dash, I, 2S4, sigma H, 2 sigma V, 2 sigma D. Okay. Now, think of a subgroup C4V. This is D4V. Huh? C4V, do you remember what would be the symmetry operations? C4V, if I say C4V, principal axis is C4, what else will be there? So, C4 square C2 will always be there, sigma V will be there, and see, you cannot call it sigma D anymore, they also become sigma V's. Anything else that will be there? E, 2C4 will be there, C2 equal to C4 square will be there, C2 dash will not be there anymore, right? C2 dash is gone, right? Because you have gone from D4H to C4V. So, that horizontal plane is gone. So, it is something like ammonia with another hydrogen, something like that, C4V, something like this. Okay? So there is no horizontal plane, no nothing. C2 double dash is gone, I is gone, S4 is gone, sigma H is gone. 2 sigma V and 2 sigma D now combine to become 4 sigma V's, isn't it? So I just show you the character table then. C4V, CE, 2C4, C2, oh they have retained 2 sigma V, 2 sigma D, fine. So this 2 sigma D is also retained, it is more of a memory of the original group, it does not become sigma V, fine, my mistake. Alright, so now what we have here in this figure is that all the symmetry operations, the characters for all the symmetry operations that are not there in C4V have been removed. Characters for all the symmetry operations that are there in C4V as well as D4H are retained. Okay. And now what we can do is, looking at these characters, we can try to see what is the symmetry species with respect to C4V. If I do not have this, if I have all the characters, then I have the symmetry species A1G, A2G, B1G, B2G, EG, etc. for D4H. Okay. When I have all the characters in between, please ask if it is confusing. Okay. Now what I am saying is, now what I have done is, I have only kept the characters for the symmetry operations that are retained in C4V. Okay. Now if I look at these lines, so what are the characters? 1 1 1 1 1 1, it has to be A1, right. So see, what was A1G in D4H becomes A1 in C4V. Okay. So I have what is called a correspondence. Remember you studied correspondence in math sometime when you were in school. 1 1 correspondence, 1 many correspondence, many 1 correspondence, remember. So now we are starting to develop a correspondence between the symmetry species of the parent group and the daughter group. Okay. What is the next one? 1 1 1 minus 1 minus 1. You can work it out or not? For C4V, what will the symmetry species be? Carefully moving the paper, it's A2. Huh? Understand? So similarly, you can work it out for everything, and this is what transpires. Is it okay now? Can you see? So what was A1G in D4H is A1 in C4V. What was A2G in D4H is A2 in C4V. What was B1G in D4H is B1 in C4V. B2G has become B2. It has lost the respect that was there because I is gone. Okay? It is not B2G anymore, it is only B2. EG is E. A1U is what? A2. A2U is A1. So don't think that you will just drop that G and U and it will become fine. Huh? See what has happened. For when you started with G, you could just drop that respect thing and you would have got the label. Here for U, not only does it lose the U, but U becomes me also. 1 becomes 2, 2 becomes 1. Alright? Got it? So now see, what you could do is, you could represent this as a correlation diagram, isn't it? Huh? A1G becomes A1, A2U also becomes A1. So what kind of correspondence is this? Many one. Let's just say many one. Okay? It's not necessarily that it's going to be many one all the time. It can be one many also. A2G becomes A2. A1U also becomes A2. Once again, many one. B1G and B2U become BU. EG and EU become E. And we have already discussed everything. So here what happens is that it is always a 2-to-1 correspondence, a many one correspondence. Because what's happening essentially is that the number of symmetry species is going down. Okay? So you get kind of a merging. So see what happens to the bases. X square plus y square and z square were the bases for A1G, and Z was the base for A2U. Since it's a many one correspondence, what has happened is that now Z as well as x square plus y square as well as z square all form bases for A1. Okay? All right? So what we can do is, using group subgroup relation, we can go down to a group of lower symmetry and consequently a smaller smaller number of symmetry operations. So the problem will be smaller, easier to handle, and then we can go back also maybe. We can try to go back to the bigger original group. Okay? That is going to be the theme of most of our work henceforth, wherever we need it, not always. But now, before going further on that, let me show you another example. C4V and C2V. C4V and C2V are also group subgroups. C2V is a subgroup of C4V. For C4V, what do you have? You have E, 2C4, C2, 2 sigma V, 2 sigma T. And C2V, everybody knows by heart, you have E, C2V, 2 sigma V. Okay. Once again, the character table of C2V is blocked out here, and this is the correlation diagram. Okay. There is something interesting here. Earlier, see what happened? The original group, the parent group as well as the subgroup both had two-dimensional representations, right? So the two-dimensional representations just became the two-dimensional representation that was there in the subgroup, isn't it? Here, however, we got a problem, because C2V famously does not have more than one-dimensional representations, right? So now what is bound to happen is that this E group is going to split. That is what is shown here. A1 1 1 1 is of course A1 in C2V. A2 1 1 minus 1 is A2 in C2V. B1 is 1 1 1 A1 in C2V. Okay. B2 1 1 minus 1 is A2 in C2V. Problem lies with E, because the characters are 2 minus 2 0. There is no 2 minus 2 0 in C2V. So as far as C2V is concerned, 2 minus 2 0 is bound to be a reducible representation. Okay? Which of course is बाएं हाथ का खेल for all of us now. We have a reducible representation, we know how to reduce it, right? Apparently it was not so बाएं हाथ का खेल for the author, so he has shown it like a bachcha. But you know how to do it, right? You can work out the coefficients and you can infer that E becomes B1 plus B2. So now when we draw the correlation diagram, this is what the correlation diagram looks like. A1, A2, B1, B2, E and here you have A1, A2, B1, B2. A1, B1 become A1, A2 and B2 become A2, and E splits into B1 and B2. So this is an example where you have many to one as well as one many correspondence. Okay. Now I want to give you a homework problem. Before that, I need to discuss a little bit. I'm digressing from that OHO problem. We'll go there, but before that, let's discuss something. See, this group subgroup relation is obviously going to be very convenient where we have large groups, right? What are the largest groups that you can think of? The largest groups are for the, no, not icosahedron. Icosahedron is complicated. The largest groups are for the simplest molecules, H2 and HCl, C infinity H and D infinity, C infinity V and D infinity H, right? So that is where this group subgroup relation is bound to be very useful. So I just want to introduce that today and give you a problem that I did not get time to discuss in the previous class. Is there in Carter's book. Right now what I am showing you is Carter's book. Please go through the problem. So how do you reduce representation of groups of infinite order? What would be the first step? I want to bring some sanity into these infinite groups. What will I do? Which symmetry operation will I try to get rid of, or which symmetry element? Definitely C infinity, right? The moment you change C infinity to a smaller c, then what you have is, in place of an infinite group, I am going to have a finite group, right? So the general practice is this: go from the most difficult problem to the easiest problem. So when you are working with D infinity H, change that infinity axis to a C2 axis. Okay, so go from C infinity to C2, largest to smallest. C1 axis is, of course, it's just E, right? So when you do this, these are the partial correlations. It has to be partial correlation, right? Because there are infinite number of symmetry species anyway. So this is the partial correlation between C infinity V and C2V. This is a partial correlation between D infinity H and D2H. Okay. So what I'd like you to do is this: they have shown you this reducible representation. Okay, and that they have been kind enough to work it out for you, to say that this is 2AG plus 2BG plus 2B3G plus 2B1U, 3B1U plus 3B2U plus 3B3U, right? Now I want to go back to the D infinity H group. What will be this breakdown? Look at this. AG is what? Sigma G plus, the totally symmetric group. So instead of AG, I am going to write sigma G plus. Please write down sigma G plus. One sigma G plus for every AG. So how many sigma G pluses do we have? How many sigma G plus symmetry species do we have? You understand the problem, right? For some problem, I have gone from D infinity H to D2H, and I have got this representation. Don't worry about what the basis is. And this has broken down into this linear sum. Okay. Now I am trying to go back to D infinity H. Okay, using this correlation diagram. Correlation diagram has to be either provided or you have to work it out. Here it is provided. Okay. So instead of 2AG, I am going to write 2 sigma G plus. What will I write in place of B2G? B2G plus B3G is pi g. Do we have B2G plus B3G here? We do. 2 multiplied by B2G plus B3G. So, it's 2 B2G plus B3G becomes 2 pi g, right, 2 pi g. So far we have got 2 sigma g plus 2 pi g. What next? 3 B1U. So, B1U can be sigma u plus, but it can also be delta u. What is it going to be? There are 3. So, it can be sigma g plus delta u also. Then there has to be an AU, right? So, you do not worry about it. So, what will it be? 3 sigma u plus, right? 3 sigma u plus. What is left? 3 multiplied by B2u plus B3u. What is that? Pi u. So, 3 pi u. So, this is how we can go from a larger group to a subgroup and pack. Okay. This is the answer that you must have got. Sigma r equal to 2 sigma g plus 2 pi g plus 3 sigma u plus 3 pi u. Okay. Now, with that background, I would like you to do some self study. Page 117 to 126 is basically carbon dioxide. Carbon dioxide has sigma as well as pi bonds, right. Please take this as a self study problem. MH6 is an octahedral molecule, OH point group. I have been kind enough to tell you that the reducible representation in using the 6 1s orbitals on the hydrogen atoms gets broken down into A1G plus EG plus T1U